Hey everybody, I'm going to talk about a couple of exercises in the book that may have proved troublesome for you. And these are things that maybe we can figure out for ourselves if somebody locks us in a room for a month and we have nothing else to do but try to work on these exercises. Uh, But if we're not locked in a room for a month with nothing else to do but work on these exercises, we're probably not going to know exactly how to do these exercises. One type of exercise is the type above, where we have limit as x goes to plus or minus infinity, and there's a radical either in the numerator or the denominator. Before I work this example out, we're going to have to make some preliminary observations. The absolute value of x. We've worked with this before. We probably saw it in high school. And we've probably also seen this in pre-calculus algebra and trig if we took that course. If you're like me, you probably saw this definition and don't even remember that you saw it. I'm sure I saw this definition when I was taking Algebra 2 in high school, maybe even when I was taking pre-calculus algebra and trig. I don't remember seeing it. And probably the reason I don't remember seeing this definition is because after we covered the topic, we never had any reason to use this definition again. So I quickly forgot that I ever saw it. Now, it is possible that maybe some of us have never seen it. Could be. We do have a concept of absolute value. The absolute value of a positive real number is just the number itself. If we want the absolute value of a negative real number, we just make it positive and we have the absolute value. The problem comes when we have to compute the absolute value of a variable or the absolute value of some expression that involves a variable. We have the absolute value of something that isn't just a real number. And because of that, we have to have a definition like this. Now, let's put this to the test and just see if it works. So we'll start with this. X equals 3. And according to the definition, the definition says if x is greater than or equal to 0, and we want the absolute value of x, then the absolute value of x is just x, the number itself. Well, here, x is 3, and it's greater than or equal to 0. This is greater than or equal to 0. And if we want the absolute value of something that's greater than or equal to 0, it's just the number itself. Well, that seemed to work okay. But what happens if we tried this with a negative number? So let's try another example. We'll try x equals -2. And we want the absolute value of -2. Well, notice that in this case, x is less than 0. We're computing the absolute value of a number that's less than 0. Our definition says if x is less than 0 and we want the absolute value of x, then we take x and we multiply it by -1. If x is less than 0, if x is negative, and we want the absolute value of x, we take x, which is negative, and we multiply it by -1 to make it positive. So let's try that. We want the absolute value of -2. So we take the number x, which is -2. We take x and we multiply it by -1. Negative times a negative is positive, and bingo, it works. Now, along with this definition of absolute value of x, I want to give you an alternate definition of absolute value of x. And this is one of those cases in math where we have, let's say, two different definitions of something. They turn out to be equivalent. And we say, well, why can't we just have one or the other? This is one of those rare cases where sometimes one definition is better than the other. Other times, the other definition is better than the first. So we're going to look at an alternate definition of absolute value of x. This is the alternate definition of absolute value of x. And the reason this works is because of the definition of the absolute value function. So up here, I'm going to bring back something to our mind. Remember what a function is. A function is a rule that allows us to plug in one real number and it gives us out one real number. We plug in a real number, one real number, and we get out one real number. And the same thing is true of the square root function. The square root of 9 is 3. And by convention, since the square root function can only give us one answer, the square root function gives us the positive root. If we want the negative root, we have to do this. Or if we want both roots, we have to do this. And think about it. We are familiar with this because in the quadratic formula, don't we have this? This is the quadratic formula, which gives us the roots of a quadratic equation, a second degree polynomial. And it should have two roots. But without having a plus and a minus here, we're only going to get one of those roots. If we want both of these roots, we have to have a plus and a minus here, so that this radical will give us both values. Otherwise, if we just have this square root is just going to give us one value because the square root function only can give us one value because a function only gives us one value. So we are familiar with the idea of the square root function giving us only the positive square root by convention. That's what the square root function does. Now, how am I going to apply this to our alternate definition? Our alternate definition says that the absolute value of x is the square root of x squared. Let's put it to the test. Let's do exactly those cases that we did before. We'll try x equal 3. And so the absolute value of 3, according to this definition, is the square root of 3 squared, and that's the square root of 9. And because the square root function only gives us the positive root by convention, this is going to be 3. So, this definition tells us that the absolute value of 3 is 3. Well, it works for positive numbers. Let's see if it works for negative numbers. So we'll try the same case that we tried before. X equal negative 2. And we have the absolute value of negative 2. According to this definition, we take negative 2 and square it. And then we take the square root. And this gives us square root of 4. And because the square root function can only give us back one answer by convention, it's going to give us the positive square root, which is 2. And son of a gun, it works. The absolute value of negative 2, according to this definition, the absolute value of negative 2 is 2. Now, which one of these definitions is better, the first one or the second one? It depends on the situation that we're in. Some situations, the first definition is better. Some situations, this second definition is better. And you know what? Sometimes we have an exercise where we have to use both definitions. And I'll tell you what, the definition that we opened the lecture with, or rather the exercise that we opened the lecture with, is exactly one of those exercises where we're going to have to use both definitions. So when we work this exercise, we'll be glad that we saw the first definition, and we'll be glad that we saw this second alternate definition as well. Okay, with no further delay, we're going to get down to business and work this exercise. And the first thing that we want to notice is that we have the quotient of two expressions. And the top is a polynomial. The second, or the bottom, is the square root of a polynomial. And we know that if x approaches plus or minus infinity, and we're computing the quotient of polynomials, we take the term of higher degree, or the term of highest degree, in numerator and denominator, and we throw everything else away. So let's do that. Limit as x approaches negative infinity. Well, there's only one term in the numerator, so I guess this is the term that we keep. And in the denominator, as x approaches negative infinity, 2x is insignificant compared to x squared. So we throw the term of lower degree away, we keep the term of highest degree, and we have left square root of x squared in the denominator. Now, does that look familiar? Square root of x squared? Hopefully it does. Square root of x squared is equal to absolute value of x. Okay, so we used the alternate definition. Now, what I'd like to do, since I see an x on top and an x on the bottom, is just cancel the x's. The only problem is I can't just automatically do that, because in the bottom I don't just have x, I have absolute value of x. So can I just automatically cancel the x's out and say, oh, we got 2? I'd like to be able to do that, but I can't. Now, think about this. X is approaching negative infinity. Can x get to negative infinity if it's not negative? Can x get to negative infinity if it never gets to the left of the y-axis? No. So if x is approaching negative infinity, we can assume that x is negative. And I'm going to write that down. Okay. So x is negative. So what? Well, that brings us to the original definition of absolute value. Remember, the absolute value of x depends on whether x is positive or negative, whether x is greater than or equal to 0 or less than 0. And remember, if x is less than 0, the absolute value of x equals what? That's right, negative x. So we replace absolute value of x with its equivalent, negative x. And let me just copy that down over here since we're running out of room on the board. And now that I'm rid of the absolute value, I can cancel. I'll divide top and bottom by x. So that gives me 1 here, negative 1 there. So I have negative 2 divided, I have 2 divided by negative 1. That's negative 2. So this exercise boils down to us computing the limit of a constant. We did that, I think, in the last lecture. The limit of a constant is what? It's the constant itself, isn't it? So this is just going to be negative 2. In recent homework exercises, there are a couple of examples. When I say a couple, maybe 3, maybe 4. No more than that, but there are 2, 3, 4 exercises like this. And we may have struggled with them. Well, if we did, there was a good reason. We had to know both definitions of absolute value to do this kind of exercise. So now that we've seen the trick, first, study this example again. Work through it as I work through it. And then the exercises in the text that are like this, work through them again the way we worked through this exercise. And it ought to make all the difference in the world. Now, there's another kind of exercise that's kind of like this one in the sense that if somebody locked us in a room for a month and we had nothing else to do but work on that exercise, eventually we'd probably figure out how to do it. But usually I tell students, Don't spend more than about 20 minutes working on an exercise if you get stuck. If you get stuck and you can't figure it out in 20 minutes or so, just ask me how to do it. And this exercise is one of those exercises. And the exercise that I'm about to do is one of those exercises too. Again, if we were locked in a room for a month with nothing else to do but work on these exercises, we might figure them out. But they are the kind of exercise that we probably won't figure out otherwise. There's a trick to doing this exercise, as we saw. And there's a trick to doing the exercise that we're about to do as well. And so in doing this exercise and in doing the exercise that we're about to do, we're going to make use of the acquired wisdom of all of those in math who came before us. In the centuries, the years and the centuries before us, people figured these things out. And the way that we get beyond the frontiers of math that exist now is by building on the foundation that they've already laid and making use of their acquired wisdom and knowledge. So this exercise and the exercise that we're about to do employ tricks that somewhere along the line somebody was sharp enough to figure out, and the rest of us are making use of it now. We benefit from the acquired wisdom of those who came before us. So let's get on with the next exercise. Okay, next example. And there are about 3 or 4 examples that look something like this in the text. And they all employ a similar approach. And if I were doing this exercise and I didn't know what the trick was, I guess the first thing that I would do is I'd look at the graph of sine of x. And so I've drawn the graph of sine of x on the board. And one thing that we notice about the sine of x is that it's cyclic. It goes up, it goes down, it goes up, it goes down, it goes up, it goes down. And it goes up and down, bouncing between -1 and +1. And it just keeps going down, up, down, between -1 and +1, off into the sunset. It just keeps on going that way, repeating that pattern and never changing. So the limit of sine of x let's see. What real number does the sine of x get close to as x goes to infinity? Okay, x is going to infinity, so we're moving along the graph this way. If we move along the graph this way, then we're moving along the graph in such a way that x goes to infinity. And as we move along the graph in such a way that x goes to infinity, we say, wait a minute, it's -1 and now it's 0, and then it's 1, and then it's 0, and then it's -1, and then it's 0, then it's +1, then it's 0, -1, 0, 1. As x goes to infinity, there's no one real number that f of x gets close to and stays close to. This stupid graph bounces back and forth between 1 and -1, assuming all of the values in between -1 and +1. But it never gets close to any one real number and stays close to that real number. So there is no limit. This limit doesn't exist. The limit of sine of x as x goes to infinity doesn't exist. And yet, in this example, it looks like they're telling us to compute the limit as x goes to infinity of something even more complicated. The limit as x goes to infinity of sine of x doesn't exist, and they want us to compute the limit as x goes to infinity of sine of x over x? Well, how can we do that? The limit of the numerator doesn't exist. Boy, talk about people having unreasonable expectations, huh? Now, it turns out, and this is a surprising thing, it surprised the heck out of me, but it turns out that even though the limit as x approaches infinity of sine of x doesn't exist, it turns out that the limit as x goes to infinity of sine of x over x does exist, which doesn't seem intuitively obvious to me. But even if it does exist, how am I supposed to compute this when the limit of sine of x doesn't exist? Well, we have to employ a trick that somewhere somebody was sharp enough to figure out this approach. And I guess this trick has been around for at least 150 years. I don't know who came up with it. But it's a great trick. They figured it out. We're going to take the knowledge that they passed on to us and we're going to build on it. So here's the trick. We start by writing down what we sort of learned about the sine of x, which is that stupid function just goes off into the sunset, bouncing up to +1 and down to -1 and up back and forth between -1 and +1. Well, we're going to write that down in an inequality. And so here's what we do. We make this observation. The sine of x is never smaller than -1. And it's never larger than +1. And that's something that we probably remember from trigonometry. The sine of x is sandwiched between -1 and +1. And we look at this inequality and we say, well, that's all nice and good. But we already know what the limit of sine of x is. It doesn't exist. We don't want to know about sine of x. We want to know about sine of x divided by x. Okay. So what we're going to do is we're going to take all three sides of this inequality and divide by x. And in case you're wondering about the signs of the inequality, since x is approaching positive infinity, we can assume that x is positive. So we just divided all three sides of this inequality by a positive number. The signs stay the same. And this looks pretty good. This is starting to look like what we're dealing with. It involves the sine of x divided by x. And we say, well, this is looking pretty good, but we're not looking for the sine of x divided by x. We're looking for the limit as x approaches infinity of the sine of x divided by x. So We take all three sides of this inequality, and let me move this arrow back a little bit. It's a little bit too close. Yeah, let me put it there. We take a look at all three sides of this inequality, and we compute the limit of each part of this inequality as x goes to infinity. So we have limit as x approaches infinity of -1 over x, and we have limit as x approaches infinity of sine of x over x, and we have limit as x goes to infinity of 1 over x. Okay, this is the expression that we want to evaluate. And notice something. As x goes to infinity, we have big number. No, that's not right. As x goes to infinity, the denominator is going to get huge. So we have little number over big number, where the denominator is getting bigger and bigger. So a limit where we have little number over big number, that's going to go to 0, isn't it? And oh, what about this negative sign here? Well, the limit of this expression is the number that this expression is approaching. And this expression, even though it's negative, is approaching 0. So that's the limit. Over here, we have a similar situation. X is going to infinity, so the denominator is going to infinity. It's getting huge. We have a limit where we have a little number divided by a huge number, and the denominator is getting bigger and bigger and bigger. So this expression is also approaching 0. That's the limit. And now, wow, what can we conclude from this? Let's see. We get 0 less than or equal to limit as x approaches infinity of sine of x over x less than or equal to 0. Well, this is somewhat of an enigma. The expression that we want is greater than or equal to 0, but it's also less than or equal to 0. How is it possible for this thing to be greater than or equal to 0 and less than or equal to 0 at the same time? The only way that that can happen is if this is 0, right? We have something that's sandwiched between 0 and 0. That is only possible if the expression equals 0. So that's our result. And I wanted to show you these things in a video because, like I said, unless we're locked in a room for a month with nothing else to do but work on these two exercises, chances are we're not going to figure it out. And there's no reason why we should spend days and days and days working on something like this. It's nice to try, but when we get to the point where we're not making progress, the best thing to do is to ask somebody. And in this case, we're asking somebody maybe who lived 150 years ago who just had a flash of insight and figured out how to do exercises like this. And now that we've seen the trick, we take that trick and make it part of our mathematical repertoire. And we're building on the acquired wisdom of those who came before us. Okay. Go back in the assignments and look for the exercises like these. Study these, and then go back and work on the exercises. Doing this sort of thing will make us better mathematicians. New stuff coming probably tomorrow.